Welcome to this presentation. In this presentation, let us have an insight of pattern multiplication. Let us consider two non-isotropic sources. The simplest case of non-isotropic sources is when two short dipoles are superimposed over the two isotropic point sources separated by a finite distance. If the field pattern of each source is given by E0 is equal to E0 dash into sin phi, then the total far field pattern at point P becomes Et is equal to 2 E0 cos I by 2. This is equal to 2 E0 dash sin theta into cos I by 2. Normalizing by setting 2 E0 as 1 gives the field pattern of the array as E is equal to sin phi into cos I by 2, where psi is equal to dr into cos phi plus delta. The word non-isotropic is similar to isotropic here is used to indicate the variation of the absolute angle of both amplitude and phase of the field is the same. The maximum amplitudes of the individual sources may be unequal. If they are also equal, the sources are not only similar but are identical. So let us consider this case where in which the sources are identical with the modification that both sources 1 and 2 have field patterns given by E0 is equal to E0 dash into sin phi. So the result is same here. Okay. This result is obtained by multiplying the pattern of individual source, that is sin phi, by the pattern of two isotropic point sources, that is cos I by 2. If the similar but unequal point source have patterns and the total normalized pattern is given by E is equal to sin phi into square root of 1 plus a cos I the whole square plus a squared into sin squared psi. Here again, the result is the same as that obtained by multiplying the pattern of the individual source by the pattern of the array of isotropic point sources. So these are the examples illustrating the principle of pattern multiplication, which may be described as follows. And before that, this pattern multiplication Et can be written as E due to reference source into array factor. So this leads to the principle of pattern multiplication for the array of identical elements. So in general, the principle of pattern multiplication can be stated as the field patterns of an array of non-isotropic but similar point sources is the product of the pattern of the individual source and the pattern of an array of isotropic point sources having the same locations, relative amplitudes and phase as the non-isotropic point sources. The individual non-isotropic source or antenna may be of finite size but can be considered as a point source situated at the point in the antenna to which phase is referred. This point is said to be the phase center. If the field of the non-isotropic source and the array of the isotropic sources vary in phase with space angle, have a phase pattern which is not constant, the statement of the principle of pattern multiplication may be expanded to include this more general case as follows. The total field pattern of an array of non-isotropic but similar sources is the product of the individual source pattern and the pattern of an array of isotropic point sources, each located at the phase center of the individual source and having the same relative amplitude and phase, while the total phase pattern is the sum of the phase patterns of the individual source and the array of the isotropic point sources. So the total phase pattern is referred to the phase center of the array. The total field can be now written as E is equal to f of theta comma phi into capital F of theta comma phi angle fp of theta comma phi plus fp of theta comma phi, where the first term indicates the field pattern and the second term indicates the phase pattern. F of theta comma phi is equal to field pattern of individual source, where fp of theta comma phi is the phase pattern of the individual source. Capital F of theta comma phi is the field pattern of an array of isotropic sources. Capital FP of theta comma phi is the phase pattern of an array of isotropic sources. So this expression, this pattern are expressed as a function of both polar angles to indicate that the principle of pattern multiplication applies to space patterns as well as to two-dimensional cases that have been considered. So to illustrate the principle, let us apply it to two special modifications. Say for example, Assume two identical point sources separated by a distance d, each source having the field pattern which is obtained by two short dipoles. Let d is equal to lambda by 2 and phase angle delta is equal to 0. Then the total field pattern is given by capital E is equal to sin phi cos of pi by 2 cos phi. So this pattern is the product of the individual source pattern sin phi and the array pattern cos of pi by 2 cos phi. And the pattern is sharper than it was in the case for isotropic source. So in this instance, the maximum field of the individual source is in the direction of phi is equal to 90 degree, which coincides with the direction of the maximum field for the array of two isotropic sources. And let us consider the next situation in which d is equal to lambda by 2 and delta is equal to 0, but with individual source patterns, E naught is equal to E naught dash into cos phi. This type of pattern might be produced by short dipoles oriented parallel to the y-axis. Here, the maximum field of the individual source in the direction of a null from the array, while the individual source has a null in the direction phi is equal to 90 degree of the pattern maximum of the array. By the principle of pattern multiplication, the total normalized field is given by E is equal to cos phi into cos of pi by 2 cos phi. The total array pattern in the xy plane is the product of the individual source pattern cos phi and the array pattern cos pi by 2 into cos phi. The total array pattern in the xy plane has 4 lobes with nulls at the x and y axis. The above examples illustrates two applications of principle of pattern multiplication to arrays in which the source has a simple pattern. However, in more general case, the individual source may represent an antenna of any complexity, provided that the amplitude and phase of its field can be expressed as a function of angle. That is to say, provided that the field pattern and phase pattern with respect to the phase center are known. If only the total field pattern is desired, the phase patterns need not be known provided that the individual sources are identical. If the arrays in the above examples are part of still larger arrays, the smaller arrays may be regarded as non-isotropic point sources in the larger array. Another application of principle of pattern multiplication yielding the complete pattern. In this way, the principle of pattern multiplication can be applied n times to find the patterns of arrays of arrays of arrays. So pattern synthesis can also be found by the pattern multiplication. So the pattern multiplication is of great value in pattern synthesis. By pattern synthesis is meant the process of finding the source or array of sources that produce a desired pattern. Theoretically, an array of isotropic point sources can be found that will produce any arbitrary pattern. This process is not always simple and may yield an array that is difficult or impossible to construct. A simpler and less elegant approach to the problem of antenna synthesis is the application of pattern multiplication to combinations of practical arrays. The combination which best approximates the desired pattern being arrived at by a trial and error process. And to illustrate the application of pattern multiplication, let us consider a hypothetical problem like a broadcasting station in the 500 to 1500 kHz frequency band requires a pattern in the horizontal plane, and it requires that is a pattern on the horizontal plane fulfilling the conditions indicator, and the maximum field intensity with a little variation as possible is to be radiated in the 90 degree sector between northwest and northeast. Let us consider this case. Right. No nulls in the pattern can occur in this sector. However, nulls may occur in any direction in the complementary 270 degree sector. But as an additional requirement, nulls must be present in the due east and due southwest directions in order to prevent interference with other stations in these directions. So, an idealized sector shaped pattern fulfilling these requirements is to be considered, and the antenna producing this pattern is to consist of an array of 4 vertical towers. The currents in all towers are to be equal in magnitude, but the phase may be adjusted to any relationship. There is also no restriction on the spacing or geometrical arrangement of the towers. Since we are interested only in the horizontal plane pattern, each tower may be considered as an isotropic point source. The problem then becomes one of finding a space and phase relation of the 4 isotropic point sources located in the horizontal plane which fulfills the above requirement. The principle of pattern multiplication will be applied to the solution of the problem by seeking the patterns of two pairs of isotropic sources which yields the desired pattern when multiplied together. First, let us find the pair of isotropic sources whose patterns fulfills the requirements of broad lobe of radiation with the maximum north and a null southwest. This is called a primary pattern. Two isotropic sources phased as an N-fare array can produce a pattern with a broader major lobe than when phased as a broadside array. Since a broad lobe to the north is desired, N-fare arrangement of two isotropic sources in the vertical axis will be tried. So from a consideration of a pattern shapes as a function of separation and a phase, a spacing of lambda by 4 and 3 lambda by 2 appears suitable. So accordingly, let D is equal to 0.3 lambda, then the field pattern for the array will be given as E is equal to cos psi by 2, where psi is equal to 0.6 pi into cos phi plus delta. For that to be a null in the pattern, phi is equal to 135, and it is necessary that phi is equal to 2k plus 1 into pi, where k is equal to 0, 1, 2, 3 and so on. So by equating these values, we can obtain the solution, and the complete array is obtained by replacing each of the isotropic sources with the secondary pattern by the two source array producing the primary pattern. The midpoint of each primary array is its phase center. So this point is placed at the location of the secondary source. The complete antenna is then a linear array of 4 isotropic point sources, where now each source represents a single vertical tower. All towers carry the same current. The current of tower 2 leads tower 1 and the current of tower 4 leads tower 3 by 104 degree, while the currents in tower 1 and 3 and 2 and 4 are in phase opposition. So the relative phase of the currents by the vectors can be given, and the solution obtained is only one of the infinite number of possible solutions involving 4 towers. It is, however, a satisfactory and practical solution to the problem. Thank you.